Hello students, so today we'll discuss about tunnel magnetoresistance. In short, it's called TMR. Now, TMR is a magnetoresistive effect that occurs in uh, magnetic tunnel junctions. MJTs. This is a component consisting of two ferromagnets separated by a thin insulator. So there will be two ferromagnets and there will be a thin insulator in between. This is what makes a magnetic tunnel junction. Now, if this insulator is thin enough, that means few nanometers, uh, electrons can tunnel from one ferromagnet into the another. So there is a tunneling possible between one ferromagnet to another of the electrons, which is actually followed in classical physics. Now, these magnetic tunnel junctions are manufactured in thin film technology, so we need to have a deposition of thin films to be occurring, and on an industrial scale these are mainly produced by magnetron sputtering. Or it can be also be done by molecular beam epitaxy on a laboratory scale and pulse-dated deposition and electron beam deposition. So these are done in the lab scale, whereas for the industrial, as we have told, it is done by magnetron sputtering. And the junctions are again prepared by photolithography. Now coming to the mechanism, and the direction of the two magnetization of the ferromagnetic film can be switched. That means if the magnetizations are in parallel, for example, then the electrons will tunnel through insulating film. So if the ferromagnetic, suppose you have two ferromagnets, ferromagnetic 1, insulating layer, and ferromagnetic 2, this is the insulator. If the magnetization directions are parallel, that means if this is magnetization is in this direction and also this in this direction, then the electrons will tunnel. Then the possibility of tunneling electron is there. If other one they are in opposite direction, that means if maybe this is in this and this one in there, then there is no electron tunneling that will take place. So it acts as a switch. So this is what is can be considered as a switch for the electricity to flow. Now, this effect was originally developed in 1975 by Jules Day, the University of Rennes, France, and they used uh, iron, rare earth metal, and copper junctions, and the temperature was kept at around 4.2 Kelvin. Now the relative change of resistance was around 14%. The relative delta R percentage was 14%, and it did not attract that much attention at that time, but later on in 1991, Miyakazu University of Tokyo actually rekindled this thing, and University of Tohoku, sorry, not Tokyo, again rekindled this, and it found that the effect is around 2.7% at room temperature. So this is quite a significant contribution. So it actually happens in this way that if say you have a ferromagnet like this, and there is a ferromagnet like this, and the electron has got both particle and wave nature. So suppose, considering the flow of electron in this direction, and these are where the insulator atoms are there. So the electron tunneling through the ferromagnetic junctions will undergo scattering. And this, let's say this insulator is mainly Al2O3 alumina. Whereas if we use magnesium oxide, then there would have been no scattering, and instead of that, it would have been a coherent transfer. That means only the electron would have traveled smoothly from the first ferromagnet to the next ferromagnet. So the nature of oxide also plays a very important role. It's not nature of oxide, but how the molecules of the oxide are placed. So that is why MgO was preferred as a insulating barrier, and tunnel magnetic resistance can reach several thousand %. So they actually made a tunnel magnetic junction consisting of the following composition: Fe, magnesium oxide, then FeCO 001. Later on, only FeMgO Fe junctions were also made, and it reached TMR of 200% TMR at room temperature. Now, the reason that AL2O3 is not giving a better performance is mainly because of the fact that AL2O3 is amorphous, and magnesium oxide, on the other hand, is amorphosity is much less than the case of magnesium oxide. Magnesium oxide has got a crystal structure, so that is why due to this amorphosity the scattering is much more predominant in Al2O3. Now these coming to the applications, the read heads of modern hard disk drive, read heads of HDDs has got a significant contribution from this TMR, and these are based on Manhattan junctions, and also they are the basis of magnetic random access memory. Is a typical of non-volatile memory, okay. And they can be also used in thermal assisted switching. It's called TAS, and spin torque transfer. These are the phenomena on which several companies are working to get further good sensors, to make good sensors.